Hi everyone, thank you for joining. So my name is Johan. I've been working on the Linphone project for now 8 years, mainly on everything regarding security, encryption, and this kind of stuff. So the agenda quickly will review the security requirements to implement something that we want. That means encrypting instant messaging. Then we'll have an overview of the protocol we use. Then how it integrates with Linphone, and at the end we'll focus on the dreadful man-in-the-middle attack. So a quick introduction, if you don't know, Linphone is around since now nearly 20 years. Is available on any kind of platform, Android, iOS, desktop, Windows, Mac, Linux. And it uses SIP standards, so it's interoperable with other SIP phones, to provide audio, video call, conferences, and messaging, instant messaging, always using SIP standards. 2 years ago, Simon Morla made a presentation about how we integrated the SIP standards to make group chat messaging. It's available on FOSDEM website if you're interested in. You'll get more details on it. So Linphone's team also provide FlexiSIP, which is a SIP proxy, which basically routing all the messages in the call operation. And also, you can use, if you want to try it, I encourage you to do that. You can use the free SIP service on linphone.org. So, what are the major security requirements for encrypting messaging? So, first of all, we obviously need to protect our data. So, we need to end-to-end encryption our content, which means the encryption is done on the sending device and decryption is done on the receiving device. So the server operating the service shall not be able to decrypt your data. This is kind of basic. Then you also need to be able to know who is sending you a message and to be sure that the message was actually intended for you, which is another point, because you can receive a message and someone pretends to be someone else. So this is another thing, another layer of security we want to add. And then there are two major features, which are if your key at some point your phone may be compromised, you want to be sure of two things. First, that if your past conversation were registered, maybe like you are living in a dystopian future where some huge organization are registering all the data stream on the internet, hoping to decrypt them later. So if your phone is compromised, you want to be sure that your past conversations are still secure. They won't be able to decipher them. And so this is called forward secrecy. And then you have another property, which is called future secrecy, which means that if your phone is compromised, you want to be sure that you will just lose confidence in few messages, and that if you continue your conversation with peers, it will get back on a safe level of encryption. But the attacker won't be able to decrypt them. Okay, and then one last but major feature of a security protocol is that it has to be accessible for users. If users have to make efforts to use it, they won't use them. If it's too complicated, they just won't do it, and they won't use your product or your protocol, and then it's useless. Oops, sorry. So we made the first attempt on that back in 2014, but which was working quite well as of for end-to-end encryption, authentication of user, but we had only forward secrecy. We lacked a good feature on future secrecy, and most of it was not really adapted to group chat messaging. Why? Because at that time, Linphone were not providing it. So we had to rework that to make something better. And so after a quick survey, we decided to use the Signal protocol that you may know, which is used by obviously the Signal app, but also numerous other applications, like for example WhatsApp is using it. Why we decided to use it? Because it had all the features we needed, most of them. It's very well documented, the protocol itself. You have an open source implementation that you can that is freely available. And it has a lot of reviews, as there are large deployments, so many people studied it, and I mean, no one found a flaw for now, so it's supposed to be safe. What we've done is we needed to, so the Signal protocol is aimed to encrypt message from one device to one device. It's not really good for encrypting on multiple device per account or group messaging. So we had to extend it, and also it's like an easy way to authenticate each other. So we had to add that. So, so now for some simple scheme, how it works basically in real life. We have two users with their device. We need a SIP proxy to route messages and to manage accounts. And we also need a public key server where we will publish some keys. So what we'll do first, Alice installs the app and creates an account. When she does that, she will push on the public key server some public keys. Well, there are some details, I'll just skip that, but anyway. And then at some point, Bob wants to establish a session with Alice, but Alice may or may not be online. That's why she needs to push first our keys on the server. So Bob will ask the server for Alice keys. Server gives them. Bob then will create a LIME session. LIME is the acronym of Linphone Instant Messaging Encryption. A session to talk with Alice, then encrypt the message, send them to the SIP proxy, which will then, if Alice is online or when Alice will come back online, will route the message, encrypted message, to Alice with some data enabling Alice to initialize the session. Okay? So Alice will create the session and decrypt the message. So far, so good. It's seems quite easy. And then she can answer back. And when she answers back, she doesn't need to contact the public key server because she already has a session ongoing with Bob. So now the public key server is out of the scheme because we just needed to establish the first connection. Okay? So the answer, the encrypted answer, will just go through the SIP server, and that's it. I thought I had 25 minutes, so I plan to go deep into details on the signal protocol, which is quite complicated, interesting, but I don't have time for that at the end. So I'll just skip this slide, but basically you can find them then on the FOSDEM website, which is because basically the protocol is in two parts. You have one part for establishing a session, which is this one. Basically it's a set of DFL-man and signatures implemented, and then you have another part which is encrypting the message. So the other part is slightly simpler. It's called double ratchet. Double ratchet, why? Because we have one symmetric ratchet, which is basically deriving keys, a chain of keys to get a message key, which you use to encrypt the message. That would give us the property of forward secrecy, because basically if at some point someone has access to the chain key, it will never be able to get back on time and to find the previous one. So this is one ratchet. It's called double ratchet. So you have another one, which is actually a DFL-man ratchet. So basically, each time you want to exchange messages, you will have to generate a new pair of keys, which then given a root key, which was given by the previous protocol, will help you to create the chain key to send messages. And you need then to integrate into your message your public key. So then Alice will be able to decrypt. And when she replies, she gives a new public key for her. You get it. You make a new DFL-man ratchet, which gives you the key for decryption. And you make a new one, which gives you the key for a new sending chain. Sounds complicated, but at the end, it's not that much more. If you're interested, feel free to ask some question later on or read the documentation. All right, so what we've done an implementation of this library because we are not really happy with official Signal ones. So our library is all in C++. It's obviously available on our GitLab. One of the main differences of the main that we have regarding the official Signal library is the protocol itself is designed to be used either with curve 259 or curve 448. Which are two levels of security. Basically, one is set to have the same level of security of AES to 128 bits, while the other one is higher security level, which the equivalent of AES 256 bits. And so our implementation allows you to use either one. The implementation also, even if it was driven to be integrated in Linphone, is aimed to be usable with anything. So there is nothing related really to Linphone inside the library. Basically, you can use it with anything which route messages, provide unique identifier for devices. And you'll need also to manage a connection to the key server. So how it integrates in Linphone? So we need, as I said before, device identification. So the Linphone ecosystem is based on SIP. SIPs will give us user address. And through the GRU, which is an RFC defined, we have device address. So this is one thing we needed. We need also the Flexi SIP proxy. We will manage these devices, manage the groups, the conferences, and route all the messages for us. And we need a secure connection to our different server, which is done using TLS and digest authentication. So now for more accurate data flow. So let's say Alice and Bob have, first they start with one device because they want to try Linphone. They heard about it at FOSDEM and they think, wow, it's cool, let's try it. So they install it. When they install it, they register on the SIP proxy and they also publish their set of public keys. And now Bob wants to talk with Alice. So Bob will create a chat room. So he'll say that to the server, so the SIP proxy, and the SIP proxy will say, okay, I want to chat with to create a chat room with Alice and I. So the SIP proxy will answer with a list of devices which are in this chat room, which for now are only 2. And so Bob will say, okay, I don't have Alice one public key, so I have to ask them to the server, which it does. Server answers the keys. We get an encrypted message, and it's it. So now things are a bit more complicated. Is that both Alice and Bob really like Linphone, so they install them on several devices, maybe their desktop, maybe their tablet, anything else. And they also convinced Carl to join their chat group. Okay, so we are Bob 1, and Bob 1 for now just has heard about Alice 1. The other devices are unknown to him. So he gets back online, and the server will push him with some notice. He say, okay, in your chat room, we have these new devices now. You have to take into account. So I say, okay, I want to send message to the chat room. I'm missing Alice 2, Bob 2, and Carl 1 devices public keys. So he'll ask just this one, the missing one, to the server. If he got all the keys, he don't need to do this step. Server answer. He sends his encrypted message, and then servers found out the encrypted message to everyone. So now how it works, because obviously the encrypted message is not the same for everyone, because everyone got his set of keys. How it works that we got our payload, which is what we want to encrypt, and we'll first randomly generate a key. This key will be used to encrypt the payload, so it gives us an encrypted payload. So far, so good. And now we'll encrypt the key using our double ratchet algorithm to everyone. Why would we do that? Because obviously the key is 32 bytes, while the message might be several kilobytes. So we'll save a lot of space doing this kind of stuff. Here you'll see that our message includes the payload once, and then for Alice 1 we have the key encrypted for. For Alice 2 it says we have the key encrypted for and what we need to initialize the session. Same for the other device, which are new. This is routed to the server, and the server will find out the message, but only the part that they really need, they actually need, to all the other devices. Okay? So now, the other way to implement group chat would be to encrypt a key from the beginning. Sorry. Would be to encrypt the key from the beginning, send it to all our peers, recipients in the group, and then derive from this key using a symmetric ratchet for all new messages. So you will define what is called a sender key. So you'll say, okay, in this group, my sender key will be this one. I distribute it to everyone, but you will lose the future secrecy, which is given by the double ratchet algorithm. And this is a solution which is actually used by Signal and WhatsApp. But we prefer to implement this one because we thought it gives you better security, and it also gives you a complete management of the group, because each time you send a message, you will know who will be able to decrypt it. While if you send your key, then your key may be passed to someone else and you won't know. The other thing also, why we did it this way, is that the library, the encryption library, the LIME library, is completely independent of the group management in this way. So it seems easier to do it this way. So maybe someone wants to reuse it and want to apply the same scheme, it can use you can use something else. So obviously, the problem is that it won't handle massive groups because each participant have an overhead of something like 100 bytes, and you got to perform a Diffie-Hellman encryption at the beginning. So on like portable device, you can go up to few hundred devices in group. More than that, it'll start to be a bit slow. But on a desktop, obviously, you can use way larger groups. Okay, so now for the conclusion, we will focus on the man-in-the-middle attack. So what is this man-in-the-middle attack? Maybe you know it, maybe you don't. We'll go quick. So let's say that your service provider is not very friendly and want to spy on you, or is being compromised, attacked anyway. But I mean, the easiest consideration is to think that he is actually wanting to spy on you. So what you'll start same as usual. Alice will publish the keys on server. Then Bob will ask for the keys, but server won't reply with Alice's keys, but with Eve's one, pretending they are Alice. Okay? So now Bob is encrypting the message, but he's not encrypting it for Alice, he's actually encrypting it for Eve, but he doesn't know that. So we can do that, send it to the server, but server is Eve. So he got the keys, so server will easily decrypt the message, then you can re-encrypt it using Alice's key and send the message encrypted to Alice, pretending to be Bob. So Alice will get a message, and the server will give the message saying, this is Bob sending you a message, here it is. So Alice will decrypt it, and she has no way to know that actually the server did this dirty trick in the middle. So now you say, okay, what was all the fuss? You've been saying since the beginning that this protocol is super cool, secure, and actually not, because it seems so easy to break it. Because you just have to compromise the server or be the server in the middle, and you can easily spy on your users. Fortunately, this problem is very common in every public key scheme, so people have thought about it. Oops, sorry. So what you need to do is you need to create an association between your public key and your device ID. You need to be sure that if someone is sending you a message saying, this is Bob and this is my public key, you need to get a way to check that this is true. So so I just quote the signal documentation in it, which really precise that if you don't do that, basically the whole protocol is crap. You have no guarantee that you are actually talking to someone you think you are. So what is the solution implemented by Signal or WhatsApp is basically you need to find a way to check that the key someone is using is actually his key. So we'll make, if you want to help me, a quick survey. Who here, raise your hand if you have WhatsApp on your phone? I confess I do. Don't be ashamed, I won't take names, okay? So it's not everyone, but still some people are. Now who of this WhatsApp user knew that in WhatsApp you can tap your friend's name, then you got this browser profile, and then you tap again on encryption, and you get to a scheme where you got a QR code or a key fingerprint, which is basically 40 to 50 double-digit numbers, and you're supposed to compare them either by scanning the QR code of your friend with your phone, which means you have to meet physically, or you have to manage to call them and read them with this long list of numbers. Anyone? Raise your hand. So we are now 3. Okay, now 4 we are? 5? Sorry. Now who actually did it? At least once. And now we are less. And now who actually did it with all his contacts? And who trace, because WhatsApp won't tell you if you did it or not. So you have to trace it yourself. You have to know, okay, this one is secure, this one is not. So basically no one. So no one is using this feature. So the whole protocol is actually, it's nice, well designed, but it's not usable, really usable. You cannot be confident on the security of your WhatsApp messages, even if it's written end-to-end encrypted. It's actually maybe end-to-end encrypted or not. So our solution for that problem was to leverage ZRTP. So ZRTP, I don't know if you heard about it. So the same problem occurs for everything, and ZRTP is aimed to solve this problem for audio calls. Basically, you're calling someone, at some point you have to agree on some keys, and so you have this key agreement protocol, and key agreement protocol is sensitive to exactly the same attack, the man in the middle, which is the plague of all key agreements protocol. And what ZRTP does is basically doing the same thing like key fingerprint comparison, but the key fingerprint is only 4 characters, which means make it way easier. And so there is an RFC, obviously, on that. We implemented this in Linphone for audio calls and video calls, obviously. Whoop, 1 minute, okay, I'll be quick. The RFC let you, let's say, extend your man-in-the-middle detection to other data. So what we've done is that we integrated in our version of ZRTP the identity key of used for the messaging encryption in order to associate them with the detection. So how it works, quickly, you make your call, you get an SDP invite. In your SDP invite, we use a custom attribute will give you the key. Then when you reply, you got the SDP to another key. You will set your key. Then you compute this short authentication string using both keys. At the end, your phone will say you, okay, you have your correspondent saying you these two characters, you say the same, and now everybody says the same thing, you're good, you accept, and your phone will store, so Alice will store Bob's key, and Bob will store Alice's key. So now we're back with our evil scheme. We have reached the keys, then they make the call, and so they actually, Bob already has just the identity key. So we'll still need to ask for the other keys to establish session. Server will answer with the Eve's public key. Bob will try to create the LM session. We'll say, oh, no, there is something is wrong here, because the key I have exchanged with Alice during our ZRTP session is not the good one. So you'll detect this way the attack. Obviously, if you do the other way around, you can also start exchanging messages and then make a call. And at that point, you will also tell you that the messages you exchanged before were using the wrong key. So you'll be noticed. And what we add in the interface is that you can easily spot the status you have with your friends. Friends can be interested, that means you are exchanging messages, but you never really check their identity. You know we are over, basically, sorry. That's it. It's how it looks in Linphone, actually. You have everything under control. A few links if you want to get deeper in it. Thank you. I have no time for questions, I guess. Sorry.